In this story, about an object we see every night and cannot explain to this day. About a body whose presence is so familiar that we long ago stopped being surprised by it. It is simply always there, up above, even and calm. But when you look closely at the numbers, at the composition of the rocks, at how its orbit moves, it becomes clear. There is nothing ordinary here. This is the story of a question that science has not definitively answered in the half-century since the first samples of lunar soil were taken. At stake is our understanding of our own origin, because this is not merely about a satellite. It is a witness to how the Earth formed, and at the same time, its strangest neighbor. Too light to be a fragment, too similar in chemistry to be alien, receding too fast to remain a fixed point in our sky. Each parameter individually can be explained, but all together they fit no single coherent model. The more refined the instruments, the more precise the isotopic methods, the louder this gap between observation and theory. Scientists propose the giant impact hypothesis, the capture hypothesis, the co-formation hypothesis, the fission hypothesis. Each explains one thing and fails on another. And the question remains, what exactly happened about 4.5 billion years ago when two bodies met in the blazing darkness of the early system and left us this quiet gray disk by which we still measure months and nights? And do you think there is a body in the solar system more mysterious than our nearest neighbor? What matters more to you, to solve the origin of distant stars, or finally to understand the very object under whose light we fall asleep? Listen, this story is about a body that by the rules should not exist, and yet it does. The satellite we observe every night has still not received a definitive explanation. Everything known about the moon suggests that in its current form, it should not exist, at least if judged by the standard models of planetary system formation. The moon remains the most anomalous body among Earth's nearest neighbors, and its presence raises questions that again and again force researchers to re-examine established ideas about the early epoch of the solar system. What surprises is not the mere existence of a satellite. What surprises are the peculiarities of its structure, composition, and dynamics. Astronomical data show that the moon has an extremely low density compared to Earth, which points to a significant deficit of heavy elements in the interior of the satellite. Such a distribution of matter usually indicates one of two things. Either the moon never formed from the same accretionary nebula as Earth, or in the process of its appearance, a separation of rocks occurred with the subsequent loss of a substantial part of the metallic component. Chemical analyses of samples returned by the Apollo expeditions confirm something unexpected. The isotopic composition of oxygen in lunar rocks is almost identical to that of Earth. This implies a shared history of matter, yet contradicts expectations. Satellites of large planets typically form from a mix with different isotopic proportions than the planet itself. It is precisely this discrepancy that became the starting point for decades of debate about how the moon came to occupy its place alongside Earth. Before seeking an answer, the question must be formulated precisely, and the moon offers 3 such questions, each refuting several theories at once. The first question concerns the angular momentum of the Earth-Moon system. It considerably exceeds the value that could be expected from standard satellite formation scenarios. This means that the rotational energy and orbital motion of the system are distributed as if an enormous initial impulse was once imparted to it. Computer simulations employing sophisticated hydrodynamic models show that standard accretion processes cannot produce such angular momentum. Its emergence requires a powerful interaction between massive bodies. The second question is the isotopic paradox. Oxygen has several stable isotopes, and they are distributed in different proportions in different bodies of the solar system. This is a kind of chemical signature of origin. If two objects arose in different regions of the protoplanetary disk, their isotopic profile will differ. but Earth and the Moon show nearly identical proportions. Such a coincidence requires either a shared history of material or a complete mixing of the matter of two bodies at some point in their early history. The third question is the composition of the satellite. The Moon contains a tiny metallic core and consists predominantly of silicates, whereas Earth has a substantial iron core. If both bodies form simultaneously in the same region of the accretion disk, the Moon should have inherited more heavy elements. Instead, a sharp difference is observed. This contradiction forced researchers to consider the idea that the Moon is the product of the detachment of Earth's upper layers. However, calculations show that for such a separation, Earth would have had to rotate at a speed incompatible with the stability of a young planet. Traditional models of satellite formation offer several mechanisms: joint accretion from a circumplanetary disk, gravitational capture, fragmentation of planetary bodies, or ejection of matter as a result of a large impact. The application of each of these mechanisms to the Moon is complicated by the satellite's specific parameters: mass, orbital dynamics, angular momentum of the system, and mineralogical composition. Each parameter creates new requirements for the model, and each model encounters new constraints. To appreciate the scale of the task, one must picture the early Earth. It was under constant bombardment from an intense flux of protoplanetary bodies. Its structure was plastic, its atmosphere saturated with gases, volcanic activity unceasing. In these conditions, the Moon could not have arisen in a calm environment. Its appearance was almost certainly linked to an extraordinary event whose traces remain forever in the tectonic memory of the planet. Three parameters, each individually admitted of an explanation, but all three together were not described by any single theory, and this is exactly what turned a familiar object into a genuine scientific mystery. Scientists decided to approach from a different angle. What if the Moon was born not from a quiet accumulation of matter, but from a catastrophe? Imagine a collision not with an asteroid, but with an entire planet, comparable in size to Mars. Earth is not destroyed, but the Moon is born from this fire. This is precisely the picture at the heart of the giant impact hypothesis, the most discussed scenario for the origin of Earth's satellite. According to this model, about 4.5 billion years ago, Earth collided with a massive protoplanetary body known in the scientific literature as Theia. It is assumed that Theia possessed a mass comparable to or somewhat less than that of Mars, and moved in an unstable orbit within the forming solar system. During a lengthy period of gravitational interactions between planetary embryos, Theia drew close enough to Earth that collision became inevitable. Calculations employing the hydrodynamic approach allow the state of planetary matter to be reconstructed under extreme temperatures and pressures. These simulations show that if Theia struck Earth at a shallow grazing angle, both objects partially broke apart. A significant portion of Earth's silicate mantle and the outer layers of Theia were expelled into near-Earth space, where they formed an incandescent disk. As the temperature of the disk dropped and its density fell, the accumulated material gradually coalesced into a single large object, the future satellite. This scenario explains several important features of the Moon at once. Since the metallic cores of both bodies remained, according to calculations, inside Earth and did not pass into the ejected disk, the satellite is naturally enriched in silicates and virtually devoid of heavy elements. The elevated angular momentum of the system also fits this scenario. A colossal collision can impart to the system precisely the initial impulse that standard accretion models lack. However, the hypothesis has a serious vulnerability related to the isotopic composition of lunar rocks. If Theia arose in a different region of the protoplanetary disk, the material of its mantle would have carried its own isotopic signature, distinct from Earth's. This would mean that lunar rocks would represent a mixture of terrestrial and foreign matter, and isotopic analysis would have detected this discrepancy. But the samples returned by the Apollo expeditions show an almost perfect match of oxygen, titanium, and silicon isotopes with terrestrial values. This coincidence is difficult to explain if a significant part of the lunar material truly came from Theia. To resolve this contradiction, it became necessary to assume that Theia formed in the same region of the protoplanetary disk as Earth. The assumption is possible, but then the next question arises. Why did two bodies of common origin differ so markedly in internal structure and orbital dynamics? An elegant hypothesis. But as soon as researchers began to calculate in greater detail, problems emerged, and not small ones. Even the best theory begins to crack when real numbers are substituted into it. Angular momentum, isotopes, disk temperature, all pointed to the fact that something was missing from the standard version of the giant impact. The first problem, angular momentum. Early hydrodynamic simulations produced a value exceeding today's observed figure. Earth, after the impact, would have had to rotate so fast that its shape would have become unstable. More detailed models propose mechanisms for losing the excess angular momentum through interaction with the solar gravitational field and tidal effects. The precise parameters of these processes, however, are still debated. They require reconciling data on the spin rate of the early Earth, the cooling time of the ejected disk, and the possible migration of the Moon to more distant orbits. The second problem, isotopes again. If at the time of impact a mixture of terrestrial and Theia material was ejected, the isotopic signature of the Moon should have differed from Earth's. But this is not observed. This pushed researchers to develop modified versions of the scenario. One such version assumes that Theia moved in an orbit almost coinciding with Earth's and struck the planet at minimal relative velocity. An impact under such conditions would eject predominantly terrestrial material rather than a mixture of the two bodies, and the contribution of Theia's matter would prove negligible. This would explain the near-perfect isotopic match. However, for the stable formation of a satellite from essentially pure terrestrial material, an exceptionally fine combination of parameters is required. The impact angle, the mass of Theia, and its trajectory must lie within a very narrow range. The slightest deviation would have led either to the reaccretion of the ejected material onto Earth or to the formation of a multitude of small fragments unable to coalesce into a large satellite. Another explanation for the isotopic match is the hypothesis that the early inner region of the protoplanetary disk was chemically more uniform than currently assumed. If material within the orbit of Mars was processed by flows of heat and radiation, and then mixed by turbulent processes, bodies from this sector could indeed have had similar isotopic signatures. And then the match between the Moon's composition and Earth's would not be an exception. This idea requires additional observations, above all data on the composition of other objects in the inner solar system. Hydrodynamic models predict extremely high temperatures in the ejected disk. A large part of the material may have been in a state of vapor and plasma. Under such conditions, volatile components should have evaporated and not made it into the forming Moon. Yet observations show that the satellite contains elements that could not have survived excessively high temperatures, indicating that the heating was less uniform than simplified models assume, or that condensation of silicates proceeded differently, or that processes acted to limit the loss of volatile substances. Some researchers propose the mathematically admissible idea of a double disk. According to this version, after the impact, the matter did not immediately form a single molten layer around Earth, but created two components, an inner dense disk of molten silicates and a more distant cloud layer of vapor. The Moon formed from the dense disk, while the vapor layer either condensed at later stages or dispersed. This would help explain the presence in the satellite's composition of elements indicating moderate condensation temperatures. An important constraint on the model is time. By various estimates, the process of the Moon's formation from the ejected disk took from several months to several tens of years. This speed was determined by the concentration of matter in the disk and the dynamics of changes in its density. Had the material coalesced too slowly, tidal interactions with Earth would have destroyed the nascent structures before they could accumulate sufficient mass. Rapid formation, on the other hand, allowed the object to maintain its integrity. Models also show that the Moon arose in an orbit considerably closer to Earth than its current position, and only gradually migrated outward, losing orbital energy through tidal interactions. Perhaps the problem is not in the details of a single impact at all. Scientists proposed fundamentally different scenarios. For decades, researchers developed alternative hypotheses. Each appeared convincing, right up to the moment it came face-to-face with chemical analysis or calculations of angular momentum. One of the oldest ideas is the fission hypothesis. Its essence is that the early Earth rotated so rapidly that centrifugal forces exceeded gravity over part of the outer shell, and a fragment of the mantle broke off, entering orbit. This hypothesis was appealing because it explained the compositional similarity. Lunar material would have derived directly from Earth's mantle. However, for such a rupture, Earth would have needed a rotation speed approaching the breaking point, incompatible with the stability of a young planet. Moreover, mantle material should contain more heavy elements than are found in lunar rocks, meaning the hypothesis does not resolve the iron deficit. The gravitational capture scenario was built on the assumption that the Moon arose as an independent body in another sector of the protoplanetary disk, and was then intercepted by Earth's gravity. The differences in the internal structure of the satellite and Earth were cited in support of this idea. However, for the successful capture of a large object, it is necessary that the body lose part of its orbital energy. Otherwise, it would simply fly past. This normally happens through resistance from a dense atmosphere, but the atmosphere of the early Earth was insufficiently dense to break an object the size of the Moon. An even more serious obstacle was the isotopic similarity. A body that arose in a different region of the disk would have a different chemical signature, and this could not be concealed. The simultaneous formation hypothesis offered a different view. Earth and the Moon arose side by side within the same condensation of protoplanetary disk material, and both bodies form from similar matter, hence their isotopic closeness. However, the model faced difficulty explaining the iron deficit. If the objects formed simultaneously in the same region, the distribution of matter should have been similar, and the Moon would have ended up with a significantly larger core. Researchers considered the possibility that the Moon's accretion occurred at lower temperatures or under conditions where heavy elements dropped out of the forming cloud more rapidly. But analogous phenomena have not yet been found in other systems. Some versions of simultaneous formation introduce the concept of a double embryo. Earth and the Moon arose as two bodies separated by a small distance within the same protoplanetary fragment, and their subsequent evolution included an exchange of material, collisions with small bodies, and a gradual divergence of orbits. This scenario can explain the compositional similarity, but requires an exceptionally fine balance of initial conditions. The slightest deviation in masses or distances would have led either to the merger of the embryos or to their destruction in subsequent collisions. A separate direction focuses on photogravitational processes under the influence of solar radiation. In the early solar system, the Sun was more active and emitted powerful flows of ultraviolet radiation that heated and ionized the surface of objects. Earth's protoplanetary disk may have experienced a gas pressure gradient that caused the migration of particles to a zone of certain temperatures, forming a kind of belt of matter. In such a zone, the embryo of the Moon could have arisen. This model, however, explains only the initial formation and does not address the questions of internal composition and the absence of an atmosphere for the satellite. The delayed separation scenario is built on the idea that the Moon formed from material that remained in Earth's orbit after the main period of accretion. Earth gathered matter from the surrounding space, and part of the material did not manage to integrate into the mantle and core. It could have formed a protoplanetary disk with a non-uniform distribution of matter. With changes in temperature, pressure, and rotation speed, this material could have separated from the planet and ultimately coalesced into a satellite. The hypothesis attempts to account for the density difference, but faces a fundamental limitation. The quantity of material capable of remaining in orbit under such conditions proves insufficient to form an object the size of the Moon. There is also the model of sequential small impacts. In this scenario, the Moon formed not from a single grand impact, but from a series of collisions of numerous bodies, ranging from several kilometers to several hundred kilometers across, with Earth at different periods. Each impact expelled material into near-Earth space, creating temporary disks. These disks could fragment, break apart, re-merge, and gradually unite into one larger object. Such a scenario explains structural heterogeneities of the Moon and the varying thickness of its crust in different regions. However, the isotopic similarity remains an obstacle here too. Even one body that formed in a different part of the protoplanetary disk would introduce a noticeable difference in the chemical signature of the satellite. For the small impact scenario to remain plausible, most such bodies would have had to arise in the same region as Earth. Some simulations point to the role of early gravitational resonances between Earth and other forming planets, conditions under which material in a certain zone of the disk concentrated at an unusual rate and could have given rise to a lunar embryo. These models require further refinement, as they depend on precise conditions in the protoplanetary disk, about which very little is known so far. Each of the alternative hypotheses explains one thing and contradicts another. All theories ultimately run into the same thing: the chemical composition of lunar rocks. It is precisely the samples brought back from the Moon that became the chief arbiter for any model of the satellite's origin. Rocks don't lie. The samples delivered from the Moon's surface by the Apollo expeditions carry the chemical signature of their birth, and this signature fits no simple model. The geochemical data together paint a picture in which every detail simultaneously confirms one hypothesis and destroys another. The most eloquent fact is the near-complete match of the isotopic composition of oxygen, titanium, silicon, and chromium in lunar rocks with terrestrial values. Such similarity is in itself paradoxical. Bodies that arose in different parts of the protoplanetary disk usually carry different isotopic signatures, a kind of chemical passport of origin. The Moon and Earth demonstrate almost identical proportions, which speaks either of a shared history of matter or of a complete mixing of the material of two bodies at some point in the early evolution of the system. At the same time, the samples show a marked deficit of volatile elements: zinc, sodium, potassium. Their content in lunar rocks is significantly lower than in terrestrial analogs, pointing to intense heating at the early stages of the satellite's formation, conditions under which volatile components evaporated and escaped from the forming body. This is consistent with a scenario in which the Moon passed through a state of incandescent disk or molten body with high surface temperature. However, the picture is complicated by the discovery in certain lunar minerals of traces of substances that could not have survived excessively high temperatures, indicating that the heating was less uniform than simplified models assume. Tungsten isotopes provide an additional reference point for understanding the chronology. They allow the moment of core mantle separation in a planetary body to be dated, since tungsten is distributed differently in metallic and silicate phases. The data show that the timing of core formation for the Moon and Earth is close. This fits with ideas of common origin or of a collision at a period when both bodies had already undergone internal differentiation. One of the key pieces of evidence for prolonged thermal activity on the Moon is the basaltic plains, the vast lava fields known as the lunar maria. Their analysis shows that magma eruptions occurred not only shortly after the satellite's formation, but continued for hundreds of millions of years afterward. This means that the moon's internal heat was preserved significantly longer than would be expected for a body of this size. The sources of this heat are debated. Radioactive decay, residual heat from formation, and a possible contribution from tidal interaction with Earth are all cited. Together, the geochemical data confirm that the moon is not a simple collision fragment, but a body with its own complex history of heating, differentiation, and gradual cooling. Chemistry told the story of origin, but about what happened inside the moon after its birth, the interior structure of the satellite speaks, recorded by seismometers, gravity maps, and analysis of magnetic properties of rocks. The moon has a core, a mantle, and a crust, but everything in this structure is not as it should be for a standard planetary body. The core is too small, the crust too uneven, and at some point a magnetic field of its own existed here. All of this together paints the portrait of a body with a turbulent and non-standard past. The moon's metallic core makes up only a tiny fraction of its total mass. This sharply distinguishes the satellite from Earth, whose iron core occupies a substantial volume and determines many of the planet's characteristics. This deficit of heavy elements in the central part of the moon is considered one of the key arguments in favor of the view that its matter derives predominantly from the outer silicate layers of a planetary body, rather than from its metallic interior. The data suggests that the core probably consists of iron with an admixture of sulfur and other light elements, which explains its low density compared to pure iron. Seismometers left on the satellite's surface by the Apollo expeditions allowed lunar quakes to be recorded and divided into two fundamentally different types. Deep tremors occur at considerable depths. They are caused by tidal deformations that Earth imposes on the inner layers of the satellite, gradually altering the configuration of the orbital system. Surface tremors have a different nature. They are caused by sharp temperature swings between the lunar day and lunar night, causing the upper rocks to expand and contract. These data show that the moon's internal structure retains the capacity to respond to external influences, despite the considerable cooling of the core. Heterogeneities in the mantle, recorded by seismic methods, point to traces of ancient melting processes. Within the mantle, it appears, there were channels through which molten material rose to the surface and filled impact basins, forming vast basaltic plains. The complex thermal history is also reflected in the distribution of crustal thickness. On the Earth-facing side, it is considerably thinner, while on the far side, it grows to nearly twice as thick. This difference does not fit models of symmetric cooling of a uniform body. Beneath the lunar maria lie what are called mascons, regions of anomalously high density, discovered through analysis of the orbits of spacecraft that experienced unexpected accelerations when flying over them. Mascons are considered to be the result of large impact events, in which dense mantle material was pushed closer to the surface and concentrated beneath the basins that formed. Maps created by the Grail mission on the basis of detailed gravity measurements revealed the distribution of these structures with unprecedented precision and uncovered beneath the surface numerous zones of varying density, traces of uneven cooling and impact processes from different eras. One of the most intriguing findings concerns the magnetic properties of ancient lunar rocks. Some of them clearly formed under conditions in which a magnetic field existed, meaning that at some point the moon possessed its own working internal dynamo. For a magnetic field to be generated, motion of molten metal in the core is necessary, sustained by convective flows. That is, the core would have had to be sufficiently hot and active. Estimates show that this magnetic field existed for several 100 million years before the core cooled, convection ceased, and the field disappeared. This duration is considerably greater than would be expected for a small cold core, meaning that the moon's internal processes were far more active than early models assumed. Possibly tidal deformations from Earth provided an additional influx of heat, sustaining the motion of metal in the core longer than residual heat from formation alone would allow. The internal structure recorded the past, and the orbit tells of how that past changed, and shows that the moon continues to recede from us right now. The moon is receding, slowly, by a few centimeters each year, but inexorably. It is precisely this movement that contains the entire history of the Earth-Moon system, including the moment when the satellite was so close to the planet that tides tore at Earth's crust and deformed the inner layers of the satellite itself. Precise data are obtained with the help of laser ranging of reflectors installed on the moon's surface by the Apollo expeditions. A light pulse travels to the satellite, reflects, and returns, and the travel time yields the distance to within centimeters. These regular measurements confirm that tidal interactions continue to pump energy from Earth's rotation into the moon's orbital motion, gradually accelerating the satellite and transferring it to a higher orbit. Earth, in the process, loses angular velocity. Its day grows slowly but inexorably longer. Extrapolating this process into the past, researchers reconstruct the picture of the early system. In the first epochs after formation, the moon was situated only a few tens of thousands of kilometers from Earth, at a distance at which tidal forces were colossal. These forces deformed the surface of the young satellite, created internal friction and heating, sustaining thermal activity, and possibly prolonging the operation of the internal dynamo. Earth's rotation in that era was rapid. Its day lasted only a few hours, and it was the moon that, gradually pulling the angular momentum of the system toward itself, slowed the planet's rotation to its current pace, a process that took hundreds of millions of years. The synchronous rotation of the moon, in which it always faces Earth with the same side, formed relatively early. Tidal braking quickly synchronized the satellite's rotation period with its orbital period, while its inner layers still retained sufficient plasticity to absorb tidal energy. The orbit, meanwhile, did not remain constant in shape. In early epochs, it was considerably more elongated, which generated periodic intensifications of tidal influence and may have sustained magmatic activity for a far longer period. The rate of the moon's recession did not remain the same throughout the history of the system. If the current pace had been maintained from the very beginning, the calculated age of the moon would be less than its actual age. This points to the fact that orbital migration proceeded unevenly, accelerating in some periods and slowing in others, depending on the configuration of the continents, the depth of ocean basins, and the rotation speed of the planet, which determine the efficiency of tidal energy exchange. The orbital history of the moon is inseparable from the climatic history of Earth. Lunar gravity acts in the precession of Earth's axis, stabilizing its tilt within a certain range and smoothing long-term climatic fluctuations. Without the moon, Earth would probably experience far sharper changes in the orientation of its axis, and consequently, far more radical climatic cycles, conditions under which the development of complex life would have been substantially more difficult. In this sense, the history of the moon's orbit turns out to be not only the history of the satellite itself, but part of the history of life on Earth. The orbit explains motion through time, but there is one more mystery that no motion fully explains. Why are the two halves of the moon so unlike each other? If you look at the moon from one side, you see one picture. From the other, a completely different world. Researchers still argue about the nature of this asymmetry, which remains one of the most acute, unsolved mysteries of lunar science. The most obvious expression of the asymmetry is in the thickness of the crust. The crust of the far side is almost twice as thick as that of the near side, and such a distribution cannot be explained by the symmetric cooling of a uniform body. Were the moon uniform at formation, the crust should have grown approximately evenly across the entire surface. The asymmetry requires either an external thermal influence directed selectively at one side, or an initially non-uniform distribution of matter in the forming body. One of the most well-grounded scenarios appeals to the thermal influence of the early Earth. In the first hundreds of millions of years, the young planet remained a blazing object with high thermal radiation. The near side of the moon, permanently facing this heat source, received substantial additional warming that slowed cooling and impeded the formation of a thick crust. The far side experienced no such influence, cooled faster, and built up a thicker crustal shell. This explanation is consistent with data on differences in radiation balance and crustal density, but requires clarification of the timescales. It is unclear whether Earth's thermal influence could have persisted long enough to create such a significant differential. Another explanation relates to tidal forces. In antiquity, when the moon was considerably closer to Earth, tidal deformations were concentrated primarily on the near side and generated internal heat through friction. This additionally impeded rapid solidification of the magmatic layers on the near side, while the far side remained relatively cold and crystallized more quickly. The most spectacular manifestation of the asymmetry is the distribution of basaltic maria. The vast lava plains are concentrated almost exclusively on the near side. The far side is virtually devoid of such structures. This means that magmatic activity throughout lunar history manifested predominantly on the Earth-facing side, whether due to non-uniform internal heating, to the influence of Earth's gravitational field on the redistribution of heat, or to a higher concentration of radioactive elements that themselves serve as a heat source. Thorium, one such radioactive element, is concentrated on the near side of the moon, forming a vast region known as the Procellarum province. If thorium and other radioactive isotopes were distributed unevenly from the stage of the moon's formation, their thermal influence over billions of years would have consistently sustained the activity of the near side. In that case, the asymmetry partly has its roots in the initial distribution of matter in the proto-lunar disk. The far side, deprived of all this activity, has preserved the most ancient impact craters and structures that on the near side were long since flooded by lava. This confirms the asymmetry of thermal evolution. The near side was constantly being remelted and renewed, while the far side preserved its primordial relief. Among hypotheses offering a fundamentally different explanation, the double moon model deserves mention. According to this scenario, two satellites could have formed in the early Earth-Moon system and subsequently collided. The merger of two bodies would have created an obvious asymmetry. One side of the combined satellite would have borne the traces of the absorbed second body, a thicker crust, different composition, fewer signs of volcanism. This hypothesis is attractive in its explanatory power, but as yet lacks convincing geological evidence. Traces of such a collision in lunar rocks have not been unambiguously identified. The asymmetry of the moon is most likely the result of the simultaneous action of several factors: the thermal radiation of the early Earth, tidal heating, uneven distribution of radioactive elements, and possibly the peculiarities of initial formation in a non-uniform disk. None of these factors individually provides a complete explanation, and this is precisely what makes this mystery particularly valuable for science. It requires a model that would account for all these processes simultaneously. The asymmetry adds yet another layer to the mystery, and while no model provides a comprehensive answer, researchers are turning to new tools, missions, instruments, and methods that were unattainable just a few decades ago. We know more about the moon than about any other body in the solar system, and yet its origin remains an open question. Each new mission does not close the mystery, but adds to it new details demanding explanation. The Grail mission created detailed maps of the moon's gravitational field at a resolution previously unattainable, revealing a complex picture of density distribution beneath the surface, mascons, zones of elevated and reduced density, traces of ancient impact structures, and uneven cooling. These maps allow formation models to be tested directly. The density structure should correspond to the predictions of one or another scenario, and discrepancies immediately point to missed processes. Spectroscopic observations from orbit detected hydroxyl groups, molecular traces of water, on the moon's surface. Their presence raises new questions. Is this water delivered by the solar wind and built into minerals, or is it a relic of ancient internal processes? If water survived in minerals from the early epochs, it means that temperature conditions in certain regions were less extreme than classical models of a hot disk predict. This indirectly supports the version of more moderate cooling of part of the ejected material. Modern isotopic methods allow the trace element proportions in Apollo expedition samples to be measured with a precision unattainable by the instruments of previous decades. Subtle variations in the isotopes of silicon, oxygen, and titanium that previously lay below the detection threshold are now measurable, and they show that the Moon is not completely identical to Earth in composition. The similarity is deep, but not absolute. These nuances carry information about the processes occurring during formation and help distinguish between competing models. The Moon has a unique status in the study of the early solar system. Its surface is not subject to tectonic processes, not swept by wind, not eroded by water. Traces of impacts, lava eruptions, magnetic signals in the rocks, all of this is preserved for billions of years without change. In this sense, the Moon serves as an archive in which the history of early bombardments, the activity of the young sun, and the conditions of inter-planet formation are recorded. Information that on Earth itself has long been erased by geological processes. Future missions aim to deliver samples from the far side of the Moon, a region that is still represented only by remote sensing data, without direct geochemical analysis. The installation of new seismic instruments on the surface will allow the satellite's interior structure to be significantly refined, to determine the precise dimensions of the core, to identify mantle heterogeneities, and to assess the level of current seismic activity. The interaction of these data with new computer simulations, employing three-dimensional hydrodynamic models, is gradually narrowing the space of admissible formation scenarios. Questions remain. The angular momentum of the Earth-Moon system still lacks a definitive explanation. The mechanism of isotopic coincidence in the presence of Theia requires additional confirmation. The nature of the hemispheric asymmetry has not been reduced to a single cause. The duration and intensity of the magnetic dynamo contradicts simplified models of thermal balance. Each of these questions is a point at which current understanding ends and space for the next discovery begins. The origin of the Moon remains a problem in which it is not enough to guess one parameter correctly. All must be explained simultaneously. Isotopic composition, angular momentum, core size, hemispheric asymmetry, traces of the magnetic field, and the history of orbital evolution. No model has yet achieved this, but that is precisely why the satellite we see every night remains one of the most intriguing objects in the history of planetary science. A body intertwined with the history of Earth itself, and yet not fully explained. Please write in the comments how you found this story. It really matters to me to know whether it held your attention all the way through and which version seemed most plausible to you. The giant impact, co-formation, or something else. And tell me, do you prefer watching in a horizontal format or vertical for your phone?